Hey folks, Sebastian from Madrigal here. If this looks familiar to you, chances are you've seen my video on using WebGPU for native games. I put out that video a little over 2 years ago, and it is by far my most popular video on YouTube. In fact, it's popular enough that it still gets regular views, and people still ask me about using WebGPU. Not to build browser games, but to use it for native desktop games. But I feel I should make a follow-up video, because the fact is, I haven't really been using WebGPU for a long time now. If you haven't seen the original video, it's called A Proper Look at WebGPU for Native Games, and I'll add a link to it below. Also, if you're wondering what happened to the game, stick around until the end, I have some exciting news for you. So to start, let's look at why I used WebGPU and what I used it for. The game you're looking at is Project Slide, a vehicular combat game I was making around the time I made the original video, using my self-made game engine called Basis. The game can still be played today, using the current version of the game engine. You can see that the game is using the D3D12 graphics API. And here's where the problems begin. D3D12 is a so-called modern low-level graphics API, which means that it expects you, the programmer, to handle a lot of the nitty-gritty details of graphics rendering. These are things like synchronization between the CPU and GPU, resource lifetime tracking, state transitions, video memory management, and so on. During this video, whenever I talk about a modern API, I mean graphics APIs like D3D12, Vulkan, and Metal. APIs that give you the best control over the rendering pipeline, but also demand the most of you as the programmer. This is a good thing because it allows capable rendering engineers to tune and tweak the graphics pipeline to fit the app or game as well as possible. But it means that small developers like myself have to fiddle with things I don't really care about. Indie game developers often simply want to use a recent, well-supported graphics API to render things on the screen. They don't need to squeeze every last cycle out of the graphics rendering hardware. So what's the problem? Can't we just use an older style API like OpenGL or D3D11? And of course that is a possibility, but those APIs are slowly becoming obsolete in favor of the more modern ones. Apple deprecated their OpenGL support many years ago, and while older Direct 3D versions work fine on modern Windows versions, tool support for older APIs is severely lacking. Also, certain things like hardware ray tracing are only available with the modern low-level APIs. And this is where, for me, WebGPU entered the picture. Even though the API was originally designed for browser use, it was, quite cleverly in my opinion, designed to also be usable as a layer between a native app or game and the platform's graphics API. The WebGPU API itself sits at a slightly higher level than the modern APIs, in that it handles things like resource lifetime tracking automatically. This means that it can feel like a more pleasant API to work with compared to the modern APIs, if you're willing to give up the few last percentages of performance and control. Another benefit of using WebGPU is that it abstracts away the different platform APIs, that is D3D, Vulkan, Metal, etc., under a single unified API. This is useful if you want your app or game to run on different platforms, as you can write your own code against a single API, WebGPU in this case, and let it handle the differences between the platforms. Before we go on, I want to stress that I'm not talking about using WebGPU for browser apps or games in this video. In the browser, you are at the mercy of the available web standards, and your options are basically WebGL and WebGPU. I've never made a browser game, so I can't really talk about that. So know that I'm only talking about using WebGPU for native games, running outside of the browser here. So why didn't WebGPU work out for me? I have two major issues using WebGPU for native games. These are things that I already alluded to in the original WebGPU video from a couple of years ago. Back then I figured I could live with these issues, but it turns out I kinda don't want to. The first issue is the complexity of building the WebGPU runtime. There are basically two popular WebGPU runtimes, Dawn and WGPU Native. Dawn is created by Google, it's written in C++, and it's used as a base for the WebGPU implementation in Chrome. WGPU Native is based on WGPU, which is used in Firefox, and it's written in Rust. Because my game engine is written in C++, I went with Dawn. And the easiest way to get it working in your native app is to follow the instructions in the WebGPU C++ guide by Elie Michel. And I'm sorry if I'm butchering your name here. I'll put a link to the guide in the description just like I did in the last video. The WebGPU C++ guide is absolutely recommended reading for anyone wanting to use WebGPU as their native game graphics API. And it's an excellent resource all around. Mr. Michel has prepared build scripts for both Dawn and WGPU Native, which makes it easier to build them. I haven't tried the WGPU Native script, but I can say with absolute certainty without the script for Dawn I would not have been using it 2 years ago. However, even with the script, the act of actually building Dawn is fairly complex. The script pulls in dependencies needed by Dawn, and sometimes the operation can fail because of some third-party repository not being available or not correctly set up. Also, the resulting library is huge. A quick run of clock command line utility that counts lines of code on the latest version of Dawn shows that it contains over 1 million lines of C++ with a total line count of almost 4 million. Now, I'm sure not all of this goes into the runtime library itself. There's 500,000 lines of raw text and almost as much XML and JSON, but this should give you an idea of the size of codebase we're dealing with here. All that to say, updating your Dawn version isn't always very quick or easy. Both Elie Michel and the folks developing Dawn itself have been nothing but nice and helpful along the way, so thank you very much for that. But after a bug or issue in Dawn is fixed, it can still take quite a lot of work and sometimes time to get it into my game. However, none of this compares to the real issue I have with WebGPU, which is the shading language, or WGSL. I'm still not sure why they decided to go with a new shading language, rather than using an existing one like GLSL, or a more generally accepted runtime format, such as SPIR-V. I've heard rumors it had something to do with Apple, possibly lawyers, but I don't know, and you should probably take all of that with a grain of salt. The bottom line though is that WGSL is a huge pain for anyone wanting to use WebGPU in a pre-existing game engine, with pre-existing shaders, materials and requirements. I showed you in the previous video the pipeline of transformations my shaders have to go through to be usable in WebGPU. I start with HLSL and convert it to SPIR-V using GLSlang validator. I then use the Naga compiler to turn the SPIR-V into WGSL, only for it to be turned back into SPIR-V when using Vulkan as the backend, or DXIL when using D3D12 as the backend. Now Dawn should in theory support reading the SPIR-V directly, but I could never get it to work properly, as certain SPIR-V constructs were outright rejected by Dawn at the time. This might work better these days. Now, as you can imagine, these transformations don't always 100% work out, and I quite often found myself debugging shaders by backtracking through the different formats only to find that one step of the transformation did something wrong or left something out. To debug shader code like this, you essentially need 3 code editors open: the original HLSL, the SPIR-V disassembly, and the generated WGSL, and then you try to mentally map one piece of code onto another. Sometimes you even had to go one step further and look at the disassembly for the generated SPIR-V, actually fed to Vulkan. Fun times. I'm genuinely impressed this worked at all. Open source projects like SPIR-V Cross and Naga are super impressive, but it is still a huge pain to work like this on a day-to-day basis, when all you want to do is to work on the game. So, with time I put less and less effort into maintaining my WebGPU rendering backend, eventually letting it bitrot away until it no longer worked. At this point I should tell you a little bit about my renderer. I used to have my own RHI or rendering hardware interface called GFX API, which all of the game code, as well as the core engine code used to draw graphics on the screen. In other words, my game didn't use WebGPU directly. Instead it used GFX API, which then talked to WebGPU. The idea was that I could support other rendering APIs too, and in fact, the main or home API for my game was always pure D3D11. So when the WebGPU backend stopped working, I simply kept running D3D11 and was able to keep working on the game that way. D3D11 was always the ground truth graphics API to me, with other backends such as WebGPU or Metal being more experimental ones. D3D11 is essentially the perfect level of complexity for me personally, and I'd be happy to keep using it until I retire. However, these days all the cool new debugging and profiling tools more or less expect you to be using a modern API, which means I can't really stay in D3D11 land forever. Not to mention, of course, all the fancy new techniques such as hardware ray tracing aren't available with D3D11 at all. It was at this point that Nolram on the Madrigal Games Discord server name-dropped another library called NVRHI. You should all go join the Discord server, by the way. It's a very cool place to discuss things like this, and we are a very chill crowd, so regardless of your level of expertise, you're welcome. Link below. You all know I eventually switched to NVRHI, and you might be wondering, did it solve all of my problems? How good is it? Well, it's so good I ended up ripping out the GFX API layer completely, throwing out both the WebGPU backend and the D3D11 backend, which as I said I was kind of betting the farm on, and integrating NVRHI at the very core level in the engine. But before we go any further, we should talk about what NVRHI is. Also, if you're interested in using NVRHI yourself, be sure to stay until the end of the video, as I'll give you some tips for how to get started. Alright, so here we are on the NVRHI GitHub page. I'll put a link to this in the description below as well. You can see we find it under NVIDIA RTX, NVRHI. It is MIT licensed. It's written almost entirely in C++. So what is this thing? Well, it's a library that implements a common abstraction layer over multiple graphics APIs, D3D11, 12, and Vulkan 1.2. Now let's just quickly go over some of these features here. So the first two relate to what I said about having to worry about every single detail of the graphics pipeline. And essentially not wanting to do that if you are a small indie developer. So NVRHI gives you automatic tracking of resource states and barrier placement, something that is, however, optional. That's a very powerful thing to have. I'll talk a bit more about the optionality of this later. Automatic tracking of resource usage and lifetime, deferred and safe resource destruction. This is something that D3D11 already give you essentially out of the box. D3D12 and Vulkan, they don't. So this lets you use these two while essentially working on the level of this one. NVRHI also supports parallel command list recording and multi-queue rendering. This is if your renderer is multi-threaded. You can record command lists on multiple threads. You can use multiple queues. That's something that WebGPU doesn't do, as far as I know. Validation layer and resource reflection for easy debugging. Especially this validation layer part here is very, very handy. So D3D12 and Vulkan already give you validation layer sort of error checking to make sure you're using them correctly. But NVRHI already has one of its own to help you catch sort of user errors, invalid arguments, that sort of thing. And you can have them on both at the same time. So it gives you quite a flexible sort of safety net, if you will, for figuring out issues. If you are interested in using this, you should definitely look through the tutorial, followed by the programming guide. So the tutorial is really a step-by-step tutorial on how to actually get started using this thing. And many of the features and concepts presented here are then explored in further detail in the programming guide, which is a bit more sort of theoretical, but goes into more detail about all kinds of things. So definitely do check these two out if you want to give it a go. So in the end, I think the main difference between WebGPU and NVRHI for me is that while WebGPU happens to work kinda okay as an API abstraction layer, NVRHI is specifically designed for that. Let's look at some pros and cons of using NVRHI versus WebGPU. Starting with the cons, as I want to end on a high note. First of all, WebGPU, while not officially stable yet, is a W3C standard, which means that it is probably going to be more stable and supported eventually. NVRHI, on the other hand, is a project built by NVIDIA rendering engineers, and they decide the direction of the project. Not that I think it very likely, but they could one day decide to take the project in a direction I don't like. Though if that happens, I could just fork the project and maintain it myself. It's a much smaller library after all. NVRHI also has a much smaller online community compared to WebGPU, and you might have to dig a bit further to get help, or figure it out yourself. Another thing is that NVRHI doesn't pretend to be its own graphics API, the single feature set like WebGPU does. There are certain things that just work differently depending on which actual graphics API you're using under the hood. For example, explicit memory heaps isn't supported on D3D11, and you'll just get a runtime error if you try to use them. Now this can be spun as either a bad or a good thing, depending on how you look at it. NVRHI also doesn't support Metal, which is somewhat understandable as NVIDIA isn't all that invested in that graphics API to my knowledge. However, I've heard that adding a Metal backend to NVRHI yourself isn't a huge amount of work. So those would be the cons. Let's look at the pros. As I alluded to above, the library is much smaller. Running clock on the NVRHI folder shows us that it isn't even 1/8 the size of Dawn. The code is also very nicely organized and written, and to top it off, it's also a lot easier to build. Essentially, you just get the latest changes from GitHub and build the library using CMake. NVRHI also supports new rendering features like ray tracing, bindless rendering, mesh shaders, etc. Essentially everything I, as a mostly solo indie developer, might want to try out, I can do with NVRHI. When it comes to helping with the complexities of modern APIs, NVRHI takes care of almost everything WebGPU does, but it allows the user to pick and choose what to manage themselves. For example, if a texture is only ever going to be written to during the startup sequence of the game, and left as a read-only texture after that, the NVRHI API allows you to specify that. That means that NVRHI won't have to track resource states for the texture once it's set up, since it's only ever going to be read-only. By setting up your resource states like this, you'll free up time that NVRHI would otherwise be spending tracking the resource states. On the other hand, if you have a texture which is written to and read from multiple times per frame, NVRHI is happy to track the states and transitions for that resource. Now we get to the thing that I alluded to during the listing of the cons. The fact that NVRHI fully acknowledges that we have another graphics API under the hood, something I really like. And it lets you access that API when needed. For example, I integrated HBAO ambient occlusion rendering with NVRHI by getting the raw D3D12 objects from the NVRHI backend and passing them directly to the HBAO library. And finally, and importantly considering what I said about the WGSL above, NVRHI doesn't do or expect anything special regarding your shaders. If you're using D3D12 as the backend, it simply expects you to give it shaders compatible with D3D12, and same thing for Vulkan. That means that the shader code that is actually executed on the GPU is what you originally compiled, not some 3 times transpiled monstrosity which you can barely identify as the original. So, how did it all work out? I've been using NVRHI for over 6 months now, and I couldn't be happier with the switch. I've also slowly been moving to using D3D12 as the main day-to-day graphics API, since it runs a fair bit faster, especially on AMD hardware such as the Steam Deck. If there is a problem with NVRHI, I can typically figure it out by stepping into the library code in the debugger and seeing where something goes wrong, and I can easily update to a newer version of the library as well. So do I recommend you switching over to NVRHI? Well, that depends. NVRHI is not a perfect replacement for WebGPU in all cases, even if it happened to be just that for me. If you're targeting the browser, in addition to native platforms, you don't really have a choice. WebGPU or in some cases WebGL are your only options. Also, if you need metal support, NVRHI doesn't have that currently, nor do I expect it to ever get official support. WebGPU does however have metal support, as does the new GPU API from SDL, the Simple Direct Media Layer. I'll put a link to the documentation for that below as well. Finally, if you're building a renderer from scratch and you're authoring your shaders in WGSL from the get-go, using WebGPU might be a perfectly fine option. In this case, you can ignore most of my complaints regarding WGSL, as long as you like working with the language itself, of course. Alright, so just like in the WebGPU video, I'm out of script and I will end this video with a little bit of discussion here. So, I promised you some tips and tricks on how to get started with NVRHI if you think it looks interesting. And since NVRHI isn't as widely used as WebGPU, you won't find as many tutorials and articles about it online. But there is another very interesting NVIDIA RTX GitHub repository. I will put the link in the description as well, of course. The donut samples. This is also MIT licensed, so you can use the code here in your own projects as long as you adhere to the license. So what is this? Well, it's a collection of samples. So for example, we have the feature demo, a demo application that shows most of the raster-based features and effects available. And this is a very sort of traditional graphics application. Almost all of these, if not all, use NVRHI Sun capacity. You can see here DX11, DX12, Vulkan, the 3 backends supported by NVRHI, so you can see which one works with which backend. And if we go have a look here on the feature demo, for example, if you've ever wondered how to fill in a texture description in NVRHI, for example, well, look no further than the donut samples. This is really a treasure trove of information regarding how to build something with NVRHI. And we have some very basic things here, like this is feature demo, but we also have ray traced shadows, ray traced particles and reflections, this kind of thing. So quite a lot of advanced topics as well. Definitely check this out. Well, what about the game? What happened to Project Slide? Well, as you can see, we can still play the game a couple of years later. This is running on the latest version of the game engine, so this is running on NVRHI rather than WebGPU. But the truth is, this never really got finished as an actual game. It's more like a tech demo than an actual playable game. The good news is that there is a spin-off project called Traction Point, which is sort of like a puzzle exploration spin-off of this very game, running on the same tech, but being written in Zig rather than C++. And about a week ago, I published the Steam page for Traction Point. And if you think it looks interesting and you would like to know more, by all means head over there, check it out, maybe even add it to your wish list if you want to help this crazy one-man passion project along. I hope to release the game in 2026, and who knows, maybe after that I'll go back to Project Slide, try to actually polish it up into an actual game. But in the meantime, do check out Traction Point, do remember to like and subscribe if you haven't done that already, and I'll see you guys in the next video. Take care!